Alright, let's dive in. Today we are talking about a force you can't see, can't touch, but it powers our entire world and even protects our planet. We're talking about magnetic fields. And this isn't just stuff for your physics exam. This is about understanding the tech you use literally every single day. So what is this incredible invisible force? I'm sure you guessed it. Magnetism. It is the secret sauce behind so much of our modern world, from the phone that's probably in your hand right now to the actual planet we're living on. But how does it really work? Let's find out. Okay, first things first. We need to get to the heart of this. What exactly is a magnetic field? We're going to define it and explore why it's truly one of the most important ideas in all of physics. So here's the main takeaway. A magnetic field isn't a physical thing you can grab. It's more like an area of influence. Imagine an invisible bubble of force that surrounds a magnet, just waiting to push or pull on any other magnetic object that gets close enough. And look, this is not just some dusty old textbook theory. This invisible field is working over time all around us. It's what makes a compass point north. It's the magic behind an MRI machine seen inside your body. And yes, it's how your phone can charge without any wires. And get this, on a planetary scale, Earth's magnetic field is our personal bodyguard, shielding us from dangerous solar radiation. It is truly everywhere. Alright, so we know what a magnetic field is and why it's so important. Now for the fun part. How does it actually work? We're about to break down the fundamental rules that run the whole show. This one's going to sound familiar, probably from way back in science class. It all comes down to a super simple idea. Every magnet has two ends, a north pole and a south pole. And the rule? You know it. Opposites attract and likes repel. That's it. That one simple rule is the foundation for pretty much everything else we're going to talk about. But wait, it's not quite as simple as just magnetic or not magnetic. Different materials have, well, different reactions. You've got your ferromagnetic materials like iron, think of a paper clip, that get yanked right toward a magnet. Then there's paramagnetic stuff like aluminium, which is only kind of interested, just weakly attracted. And then, believe it or not, you have diamagnetic materials like water that are actually slightly pushed away by a magnet. How cool is that? So here's a question. How on earth do you draw something that's totally invisible? Well, physicists came up with a pretty smart solution. Magnetic field lines. Think of them like a map. They're imaginary lines that show us the path the magnetic force takes. They always flow from the North Pole to the South Pole. And here's the key. The more crammed together those lines are, the stronger the magnetic field is in that spot. Okay, this is where things get really interesting. When you mix electricity and magnetism, like by running a current through a wire that's inside a magnetic field, you create a force, a push. And that right there is the secret behind every electric motor. So how do you figure out which way is going to push? That's where Fleming's left-hand rule comes in. It's a super handy trick. Just remember with your fingers. Field, current, force. Seriously, you have to know this for your exams. And of course, there's a formula for it. F equals BIL sine theta. Now, it might look a little intimidating, but it's not. The force, F, just depends on how strong the magnetic field is, B, how much current is flowing, I, and how long the wire is, L. But honestly, the secret ingredient here is the angle, that sine theta part. That angle is everything. It can mean the difference between getting a huge push or absolutely nothing at all. Okay, that's enough theory for now. Let's get our hands dirty and see how this stuff actually plays out in real exam questions. This is where it all comes together. Alright, let's start with a classic exam problem. We've got a coil of wire, a magnetic field, and notice that the field is changing. That is the key word right there. Whenever you see a changing magnetic field, your brain should immediately think electromagnetic induction. That's the whole idea of creating an electric current just by using a changing magnetic field. So let's walk through this step by step. First, we pull out the right tool for the job, Faraday's law. Next up, we need the area of the wire loop, and don't forget to switch those centimeters to meters. Then we figure out exactly how much the magnetic flux changed. And finally, we just plug all those numbers into the formula, do the math, and bam, 2.4 volts. See, not so bad when you take it one step at a time. Our next problem is a little more direct, but you've got to pay attention to the details. We've got the length, the current, the field strength, and there is the magic word perpendicular. Trust me, that one word makes our lives so much easier. So we go back to our first formula, F equals BIL sine theta. Now, because it says perpendicular, we know the angle is exactly 90 degrees. And the sine of 90 is just 1, which is awesome because it means we are getting the biggest possible force. So we just multiply the other numbers together and we land on our answer, 0.8 newtons. Alright, last one, and I'm going to warn you, this is a classic trick question. You really need to read it carefully. We have a particle moving parallel to the magnetic field. What's the force on it? This isn't about crunching numbers. It's a test of whether you really get the core idea. And the answer is a big fat 0. Nothing. Why? It's all about that angle again. If the particle is moving parallel to the field, the angle between them is 0 degrees. And what's the sign of 0? It's 0. So the whole equation just collapses. The particle feels absolutely no magnetic force and just sails right on through, totally unaffected. We've covered a ton of ground, so let's wrap this up with a quick recap to make sure all this stuff sticks. These are the absolute must-knows that will give you an edge in your exams. Think of this as your personal toolkit of formulas. We've already played around with the first one for the force on a wire and the third one for the induced voltage. But don't forget the others. The force on a single moving charge in the field created by a wire are super important too. Get comfortable with this and you'll be in great shape. And last but not least, a few quick tips to grab every possible point on your exam. First, units. Don't throw away easy marks by forgetting units like Tesla. Second, show your work. You can get partial credit even if you mess up the final number. And please, please, please read the questions carefully. As we just saw, a single word like parallel can change everything. So, let's leave you with this final thought. We've seen how magnetism can be used to create movement. That's how every electric motor works. But what happens if you reverse it? What if you use movement within a magnetic field to create electricity? This beautiful two-way relationship between electricity and magnetism, that's not just a cool idea from a physics class. It's literally what powers our entire world. Thanks for joining us. For more practice questions and solutions, visit examkp.com.